As we continue with this section in describing motion, we get to some terminology, and some's going to be very familiar and some are going to be new terms. But the first one is speed. Speed defined is the distance traveled divided by the time interval. So if we look at the formula for average speed, which is what we're very familiar with prior to physics, it is going to be distance over time. I do want to point out um, the notation here. So this delta or this triangle is always going to be change, how something is changing. And so your distance over how much your time changed is going to be your speed. Um, if you look at never changing direction, so if it's going the same direction the whole time, you'll see that absolute value. Remember, speed is a scalar, so it does not have direction. But this variable x is always going to be your position variable. And so that delta x is how your position changed over how your time changed. So then velocity is a vector. Remember, vectors have direction. And so the rate at which an object's position is changing is going to be that v variable. And mathematically, it is going to look exactly the same as speed. It is going to be the displacement, which will be the delta x over the delta t or the time. But velocity does take into consideration direction. And so when you're given velocity, you're going to be given the direction that it's going, not just the distance covered. So as we look at the formula for this rate of motion, the first formula we're going to look at is this velocity. This line is going to indicate average velocity. And then, of course, the delta or the change in x position, delta change in t time. So that bar is always going to indicate that average. And so if we look at a average velocity over a time period, we would just take how far it traveled divided by the time to figure out that average. Average velocity can be positive, zero, or negative. So remember, velocity is distance over time. And so as we look at a velocity time graph, we're going to see as we graph these, we put one variable down here, just like we would with an x, one variable here. So we have our time and our velocity. And so you can see this period of time, we are going 50 kilometers per hour. This period of time, we are going 0 kilometers per hour. And then you can see as we go these different spots how our velocity is changing. And so you can graph them as a coordinate pretty much. And we'll look at some other position graphs and things like that. But when you think graphing, you're going to think just like you would have done in a very early algebra math class. You have two axes in this particular case, and you're graphing the two variables on that coordinate plane. Instantaneous velocity then is different than average. It is the actual velocity at a given time. So we're talking about a specific time here, not an average. So average is going to be over the entire distance over the entire time, whereas instantaneous, you want a velocity at a specific time. And so when we look at instantaneous speed, remember speed does not include direction here. Um, Most of the time, it's not going to be sharp. It's going to be very smooth, not abrupt. And then when we find instantaneous speed, so if we're looking at our speed, it's not going to be sharp usually. It's going to be, we slow down gradually or something like that. But if we look at instantaneous, we look at this tangent line which is that line that touches at that specific point that we want to talk about. And we would look at the slope of this specific line at that point. So if this is the point in time, we want to know exactly how fast they were going or the instantaneous speed, then we would look at the slope of the line where it touches that specific point. Let's talk about the word magnitude. So the magnitude, and this magnitude here, this word you're going to see over and over when we get into vectors. Magnitude is going to be the numeric value that is given to that specific variable, whichever one you're talking about. So magnitude, you can think of like a length or a specific assignment of a number to that object or velocity or whatever you're talking about when you're talking about magnitude here. But the magnitude of an object's instantaneous velocity is its instantaneous speed, the speed at one particular moment. And so, magnitude, so for example, if we were talking about 50 miles an hour, 50 would be the magnitude of that particular velocity or speed. So let's look at the word problem here. A westbound airplane is 648 kilometers east of Houston at noon. The plane continues to fly west, and at 3:30 in the afternoon, it is 246 kilometers west of Houston. What is the plane's average velocity? So the terms east and west here, you're going to have to think of almost like you would a number line, right? And so you want to establish where you are. Remember, we considered point of reference. Point of reference is very important. And so the point of reference that they give us here is Houston. And so you want to consider the fact that you have Houston as your point of reference. It says a westbound plane is 248 kilometers east of Houston. So just like on a map, you have east and west, right? And so if it is currently 648 kilometers east of Houston, this is the location. Westbound means it's traveling that direction. It continues to fly west, and at 3:30, it is 246 kilometers west. Well, now it's right over here, 246 kilometers. So if you want to think about how far apart or how far it has traveled, which is what we need to know for velocity, then we are going to have to assign a positive negative. And so just like on a number line, typically, and it doesn't always have to be this way, but typically we are going to say, well, east is positive and west is negative. And so if this is my point of reference, that would be kind of my 0 point there. And I need to figure out velocity. Well, velocity is going to require change in position. So if we think about um, kind of our formula here. To figure out your change in position, you want to do your ending position. And we talked a little bit about this, your final position. Remember that F subscript means final position. And we want to subtract our initial position. And over that, we are going to do our final time. Because remember that is over change in time. We're going to say our final time subtracting our initial time. And so our final position then is that negative 246 kilometers because it is in the west. And then our initial is going to be our 648 kilometers. Our change in time, it's a little hard when you do it like this, subtracting, unless you use military time, it's going to look like a negative, but time is never negative. So if you did 3 3:30 minus noon in military time, 15:30 minus noon, you would see that's going to be 3.5 hours. You want to make sure that's 30 over 60. Sometimes people try to write this guy as 3.3. That is incorrect. It is 3 hours and 30 out of 60 minutes, which gives us that 3.5 hours here. And so when we subtract, we get negative 894 kilometers in 3.5 hours. When we do our division there, we get negative 255 kilometers per hour. Now that seems weird, but remember that negative just indicates direction. And so another way to write this is saying that I traveled 255 kilometers per hour to the west. And so that's all that negative means is that we were traveling west here. Now you'll notice this particular one flips direction. And so um, in this case, we have north and south. And so north and south, again, are going to uh, typically north is positive, south is negative. And so as we look at this one, it says a ship is 218 kilometers south of the equator, cruising at an average velocity of 35.5 kilometers per hour north. What is the ship's position after 7.65 hours? And so now what they've done is they've given us different variables. So we're still going to say, well, average velocity, that is going to be my change in position over my change in time. So when I think about what they've given me here, they've actually given me my average velocity. And so I'm going to plug that in. I have the average velocity here, and it is traveling north. And so I'm going to assume that north is positive. Now they have drawn it, and I'm actually going to flip this a little bit. They have drawn it with north down here. Again, your point of reference, and you have to set your parameters, but we're going to do it as though they're traveling uh, up or positive when we think of north. And so we're going to leave it at positive for this, but they are traveling kilometers per hour and they're traveling north. So they've given me that. And so it says Um, it is 218 kilometers south of the equator, all right, south of the equator. And so it tells us the current position. We do not know the final position. So remember, when we set this up, we have final minus initial. And so we do not know the final position. That's actually what they're asking. We know the initial position of 218 kilometers, and remember, it is kilometers south of the equator and it is traveling north. And so if we are south of the equator and we are traveling north, um, in my scenario, I'm going to make south negative and I'm going to make north positive. And so if they are 218 kilometers south of the equator, then I'm going to make that negative there. And then we know the time. So it says after 7.65 hours. And so what we're going to do here is we're just going to solve. We are going to multiply by that 7.65, and that will give you 271.575 kilometers. And I do want to watch these units here. So kilometers per hour, remember per, that means the kilometers is on the top here and the hours is on the bottom. And so when we look at our units, those hours would cancel each other and we're just left with those kilometers. So that's why we have just the kilometers here. And that is going to equal our final, and remember minus a minus, that's going to give us a positive 218. And then the last step here is to subtract that 218 over. So we are going to take the 218, we are going to subtract, and you're going to get 53.575 kilometers. That is a positive answer, so we know it's going to be north. But the other thing we have to look at is our significant digits. And so we're going to go up here and we're going to look at what was given to us. We have 218 kilometers, we have 35.5 kilometers per hour, and 7.65 hours. All of those are three significant digits, three significant digits. So because we were multiplying, dividing here. We want to make sure that we do that correctly. And we have three significant digits, which means we need one, two, three significant digits because this is our last one. We're going to look here and we want to say 53.6 kilometers because it's positive. I'm going to say north of the equator. So the next term we're going to look at is acceleration. Acceleration is the time rate of change in velocity. And so as we look at for acceleration, again, average acceleration, but now we're looking at how velocity changed compared to time. So in one-dimensional motion, acceleration can be positive, zero, or negative. And a zero acceleration just means the velocity isn't changing. And so if velocity is speeding up or slowing down, then um, you're going to have some acceleration changes. And so velocity will be positive. When acceleration is positive, it means we are speeding up. Velocity can be positive, meaning that you are moving. But if my acceleration is negative, that means I'm slowing down. And so they kind of do the opposite of each other. If velocity is negative, and acceleration is positive, then I'm slowing down. Because remember, velocity is representing position changing, like direction. And so these kind of negate each other. You can see that they're opposite of each other. When they're both positive, we're speeding up. When velocity is positive, but acceleration is negative, we're slowing down. But when velocity is negative, direction has changed, and then the acceleration is in the other direction, it's going to slow down and speed up, opposite of how you would think. So again, if you look at time and velocity, you're going to see your acceleration changes. And so um, that, just like time and position represented your velocity, time and velocity is going to represent acceleration. And again, instantaneous acceleration is no longer look at the average, but the acceleration at a specific point in time. So the slope of the position graph is going to be velocity. The slope of the velocity graph is going to be the acceleration. Just like we looked at the other graph with position, when we took that slope of that tangent line, we got velocity. And if we were to graph velocity, the slope there is going to represent the acceleration. So if a velocity time graph is straight, then that means the acceleration is constant. Average acceleration will equal your instantaneous, and that means it is uniformly accelerating. It is accelerating at an uniform rate. So I do want to talk about the standard unit. Remember we talked about SI units? So SI units for acceleration is meters per second squared. So your velocity is going to just be meters per second. And then your SI for acceleration is meters per second squared. And so you're going to see a lot of conversions that have to happen because when it asks for acceleration, it's going to want this meters per second squared. So to calculate acceleration, you are going to do your change in velocity over your change in time. And so that is going to require your final velocity minus your initial over that time. And so in this example, they said, what is the average acceleration for a trip downhill? Well, we are going to take our final velocity minus our initial velocity. We are going to divide it by our time. Now, here is the problem. They have given us this in kilometers per hour. And then we have a second, and our acceleration, it needs to be meters per second squared. So before we can do anything here, we have to correct our units. Cannot have kilometers per hour divided by seconds. Also, our acceleration needs to be in meters per second. So before we do anything, we need to change these two to be meters per second, and that is going to require unit conversion. So without doing two conversions, I would probably recommend that we go ahead and just do the subtraction first. So if we do the 116 minus the 5, that's going to give us 111 kilometers per hour. And that's what we need to convert. We need to convert 111 kilometers per 1 hour. And we need to convert that to meters per second. And so converting that kilometers, remember 1 kilometer is 1 1,000 meters. And then converting those hours, 1 hour is 3,600 seconds. And so remember, you can double check that. You can say, I canceled my kilometers, I got meters. I canceled my hours, I got seconds. And then you're just going to multiply across and do that conversion. And then remember that whole thing is being divided by seconds. And so dividing by 30 seconds is the same thing as multiplying by 1 over 30 seconds. That's the same thing as division. So remember, division is multiplication by a reciprocal. And so you can go ahead and add that to the end. What you'll notice is you have meters left on the top, and you have seconds and seconds left on the bottom, which looks very much like meters per second squared. So when we do this, we will have our acceleration. And so when you multiply it all the way across, you're going to get 1.027 meters per second squared. If we go back to our initial um, division here, we have our 111. Remember, we use, when we're adding and subtracting, we use decimal places. And so when we subtracted that, neither one of them had a decimal place, so we left it at no decimal places. So we have three significant digits here with no decimal places. And then we were dividing by 30. I didn't write it here, but it's 30.0 seconds. That's also three significant digits there. And so when we did that division, remember, you don't have to worry about the conversion piece of it. You just need to worry about this. Three significant digits divided by three significant digits. We need three significant digits here in our answer. So 1, 2, 3. Again, we need to look to the right, which means 1.03 meters per second squared.